Hello, I'm going to be talking about some work that we at Cambridge have done together with Cranfield and Rolls-Royce under the EU Clean Sky project ODIN to look at separation on the external surfaces of aircraft engine nacelles in certain off-design conditions. The motivation for this work is that in order to reduce the environmental impact of civil aviation, it's necessary to move to aircraft engines which have larger bypass ratios and therefore larger diameter fans. Now, if we're simply to take an existing engine design and simply scale it up, the nacelle would also grow larger in proportion, and the large wetted area would result in a substantial increase in drag, which would counteract many of the benefits of the larger bypass ratio. So it's necessary to move instead to slimmer nacelle designs, and these tend to feature higher surface curvature around the leading edge of the nacelle, which can be problematic in certain off-design conditions. Two of these off-design conditions relate to windmilling when the engine is shut down or becomes inoperative. Diversion windmilling refers to when this happens during the cruise phase of flight, whereas end-of-runway windmilling corresponds to when the engine is shut down during takeoff climb-out. Diversion windmilling, which features a relatively high Mach number and low angle of attack. If we zoom in around the leading edge and consider the capture stream tube during normal operation, we can see that the stagnation point sits somewhere around the leading edge of the nacelle on its highlight. However, if the engine were then to be shut down, then the capture stream tube would get contracted due to the lower mass flow rate through the engine, and as a result the stagnation point would move downstream inside the intake. As a result, flow now has to then pass around the highly curved nacelle surface. As it does so, it accelerates to form a supersonic region which terminates in a normal shock. And if this shock wave is strong enough, it can cause a local separation of the boundary layer developing on the external fan cowl surface. In end-of-runway windmilling, the lower Mach number means that the flow field looks slightly different. In this case, despite the flow acceleration, we don't get a similar normal shock. But despite this, the strong pressure peak can result in a substantial enough adverse pressure gradient to cause an open leading edge separation around the external fan cowl surface. So clearly, whether or not the boundary layer separates, and indeed the scale of separation, has a big impact on the performance of the overall aircraft. But despite this, we don't actually know a lot about the detailed aerodynamics involved, and in fact, the RANS computational methods typically used in industry for nacelle design aren't able to reliably predict the scale or onset of separation in these scenarios. So the goal of this work is really to perform a set of fundamental two-dimensional wind tunnel experiments that tell us a bit more of what's going on. Now, I'm not going to go through in detail the wind tunnel setup that we use for this experiment, because that was covered in an AIAA SciTech paper earlier this year. But essentially, the flow path is defined by contours within the wind tunnel test section, which are designed based on RANS computations of the full-scale three-dimensional nacelle under diversion windmilling scenarios, and care has been taken to ensure that the flow within this wind tunnel is representative of the real scenario. A key parameter in windmilling scenarios is the mass flow rate through the engine. So in order to replicate three different mass windmilling severities, we want to consider three different effective engine mass flow rates. And the way we do this is by replacing the lower wall contour in the wind tunnel with a set of three different interchangeable bumps with different heights. And as the bump height increases, it restricts the flow through the lower channel, which corresponds to the internal engine flow channel, and as a result reduces the mass flow rate through the engine. Now, for the end-of-runway windmilling condition, we can see that there's an analogous setup, and again, we've got three different bump heights which correspond to three different severities of windmilling in this scenario. And so we've now got two wind tunnel setups which allow us to investigate the flow field for diversion windmilling and end-of-runway windmilling. So let's start off by seeing what the flow looks like in the diversion windmilling condition. And we'll start off by visualizing the flow field using Schlieren imaging. And from this video, we can identify a region of flow acceleration around the leading edge of the nacelle. We can see the supersonic region that terminates in a normal shock, and we can also identify the boundary layer developing on the external fan cowl surface. As we increase the severity of the windmilling, we can see a number of differences. The shockwave has not only moved downstream, but it's also become more prominent. And where this shock wave intersects with the boundary layer, we can see that it moves from a smeared shock foot characteristic of an attached shock boundary layer interaction through to a bifurcated lambda shock structure that's typical of boundary layer separation. And accordingly, the boundary layer downstream has got thicker as a result. Now, as the windmilling severity increases, we also see differences in the Mach number distribution on the external fan cowl surface, which we measure using pressure-sensitive paint. The first thing to say is this flow field is pretty two-dimensional across the wind tunnel span. We can identify the supersonic region and the terminating normal shock. And we can also see that as we increase the severity of the windmilling, we see this supersonic region grow in size as that normal shock moves further downstream. And we can quantify this by considering the Mach number distribution on the tunnel centre line, where we see that not only does that shock move downstream as the windmilling becomes more severe, but the shock also gets stronger. And a consequence of this more downstream stronger shock wave is captured when we consider the separation characteristics from surface oil flow visualization. When I mark on regions of central and corner separation, we can see that for the mild windmilling case, the flow is attached almost everywhere. Whereas for the strong windmilling case, we now have well-developed corner separation and central separation across the entire tunnel span. These differences in separation are then also reflected in the boundary layer profiles some distance downstream of the shock wave. So for the mild windmilling condition, the boundary layer is less than 2 millimeters thick. Whereas as we consider the cases where separation is incipient and then there's well-developed separation further upstream underneath the shock wave, we can see that the boundary layer gets significantly thicker as a result. So by considering these different sets of measurements, we've got a better idea of what's really going on behind the diversion windmilling flow field. Let's now consider what happens in end-of-runway windmilling, starting again with Schlieren visualization. Here we can again see the flow acceleration around the leading edge, and we can identify the boundary layer on that external fan cowl surface. As we increase the severity of the windmilling, we can notice that looking at the lower videos, there seem to be more prominent turbulent eddies as we move from left to right. Now, in order to better understand what's going on, we take a time average of the top set of videos, where we see that indeed in all three cases, the boundary layer is attached. And so the increase in turbulent eddies that we see seems to actually be characteristic of an increase in corner separation near the sidewalls rather than fully fledged separation across the entire tunnel span. But we do want to investigate this separation, both the onset and the characteristics of the separated flow field. So to do this, we keep the geometry the same and we increase the Mach number at the entry of the test section from 0.25 to 0.3. And when we do this, we see a very different flow field. We can see that we've still got that attached boundary layer for the mild windmilling case, but by the time we get to the strong windmilling case, we've got a clear separated shear layer. And we also see similar differences when we consider the Mach number distribution on the external fan cowl surface. Again, we've got quite a two-dimensional flow field. Interestingly enough, despite the low Mach number coming in, we still get a supersonic region. And we can also identify the corner separation that we saw some indication of in the Schlieren videos. In order to better understand this supersonic region, we can again consider the Mach number distribution on the tunnel centre line, where we can see that the peak Mach number in these two cases is roughly 1.2. However, the flow field looks quite different when we consider the strong windmilling condition where separation has occurred. Here we see that there's a lower suction peak and the pressure field is more uniform due to the boundary layer not quite following the curvature of the nacelle model. We also see some asymmetry across the tunnel span. And indeed, when we consider the boundary layer profiles in this case, we can see that even before separation, we see an increase in boundary layer thickness. And once separation has occurred, we can see a very large shear layer with a clear reverse flow region. So by performing these sets of experiments, firstly on the diversion windmilling flow field, we've seen the onset of separation once the shock becomes stronger than Mach 1.4. In end-of-runway windmilling, we've seen that under the nominal conditions, the boundary layer is attached for all three windmilling scenarios tested, whereas when we increase the Mach number to 0.3 at the entry, we see a supersonic region which can result in corresponding flow separation. Thank you very much for your time.